Okay, yeah, good morning, everybody. Welcome back to 11. Yeah, so today the goal is, well, this is our last full week, as you probably are aware. So the goal this week is to get into a little bit more of the details about how you calculate torque and do a few more complicated situations with it. And then just the last class next Tuesday, we'll just be doing review for the end. So this is sort of our last topic. And so we did introduce torque a few weeks ago, and hopefully you remember at least a little bit about it. How if you have a force that can cause something to rotate, that gives a torque. And then the moment of inertia tells you how much you accelerate angularly using Newton's second law for rotation. And so today I just want to do a very brief review of the main points on that, and then we're going to start talking a bit more to do more complicated torque calculations, ones where you actually have to think about the angle that the forces act at. There's a couple other points that I wanted to bring in, like for instance, okay, so if you have some object, I want you to remember too that the force of gravity acts at the center of the object. Well, we write center of mass because for more complicated objects, you can actually have you have to think more carefully about where all the mass is arranged in an object. But we're going to stick to uniform objects, so they're just all made of one thing, in which case, when we say center of mass, you can just think center of the object. And the point is, right, for torque, it mattered where forces act as well as how strong they were, right? So for example, right, if you had like a seesaw setup where there's a beam on balanced on the point of a pivot, you get a normal force from the pivot and you get the weight from the beam, and they both act right there, right? And so since they both act right where you would rotate, then there's no torque because they have zero distance away from the axis, right? But if it was off center, even though you could think that the normal force would still be able to cancel the y direction force, right? Like we talked about back in the second unit, since it's off balance and now around that point where the normal force is acting, you can get a torque from the weight, and that will make it start to spin, right? And so you have to worry in some cases about not just the forces and their directions, but where those forces act, because that can cause the object to start moving around. Okay. Then we jump right into doing the torque calculations. So in the full detail of the torque calculation is that torque is a vector, and it's the cross product of a position vector that tells you where a force acts away from some axis, crossed with the force itself. Okay. Now for us, we're not really going to have to do full calculations of the cross product, so I'm not going to write down like a general formula for like the x, y, z components of it. The way I want you to think about it is it's just kind of the complement to the dot product that we did for work, right? So there, the dot product told you the component of, say, the force along the displacement direction, which was the work. The cross product is the complement. It tells you about the component of some vector perpendicular to another vector, right? So if I draw a triangle with the components of B along A, which is what I have in the picture here, right, then the length of one side of that triangle, so the hypotenuse is B, and the length of one of the sides of the right triangle is A dot B along A, and the other length is the magnitude of A cross B. Right? And then there's some angle between A and B. If I draw them from the same point, that's theta, and that gives you that the magnitude of A cross B is A times B sine theta. This is the way to think about it, basically. And then you could also think of it as the A on the B as well. We have to figure out the component of A that's perpendicular to B and then multiply that with B. And we brought this up last week with angular momentum as well, which is the same thing, same idea, right? That the cross product is actually a vector that points perpendicular to the two initial ones. But mostly we're just interested in the magnitude of this cross product, of this torque, because the direction just tells you which way it's going to make the thing spin, like clockwise or counterclockwise, Okay, and that's a little easier, I think, to visualize than to try to remember all the time which way the vector is going. But that direction will be more important for electricity and magnetism, so like in 212. And so I do want to bring up one way to do it. So there's this thing called the right-hand rule. This is the convention that we use to decide which direction that vector should point. And basically what you do is you have to take the way I do it, there's a couple different ways people do this, but the way I do it is you take your fingers of your right hand, your 4 fingers, and you point them along the direction of the first vector, so like A, and then B is more up, so you turn your hand so that you can bend your fingers towards B, and then your thumb tells you which direction the vector is pointing. Right, if I had done B cross A instead, B was more up, and then I had to bend towards A, and then it's pointing the opposite way towards me. Okay, so we're not going to have to practice that a lot. I just wanted to mention it. Because like I said, usually we can just visualize from where the force is acting and which direction the force is pointing, which way it's going to make a thing want to spin around the axis we picked. Right, and so these are really the main things. I've tried to break this up into it looks like a lot of things, but it's really just breaking up the detail to very, very small details of the idea. Right, so one thing is, think about when you have your picture of the force and where it's acting, which way does it want to make the thing spin? Clockwise or counterclockwise, right? And you need to pick a direction to be positive so that everything is always measured as going either counterclockwise positive, clockwise negative, or vice versa, as long as you're consistent for all the different things in the problem. You get more torque from more force or from a bigger distance, right? But the maximum that you can get away is when they're perpendicular, and then you get R times F. And if it's not perpendicular, if there's some angle, you get R times F times the sine of the angle between them. And that's always less than 1, sine of theta, right? And I actually should have made this probably as a slide, but I didn't think about it. So there's sort of 3 ways to think about how you do this. And so I tried to draw them here. So one way, if you like, the very mathematical way is this. So let's say I have a wheel, right? And I want to figure out how a force makes the wheel rotate around its axis. Right? I need to draw an R vector that goes from the axis to where the force acts. So when I draw a force, where it's acting on the picture is where the vector starts. It's the tail of the vector, not the arrow tip. That's my R vector. And then F, let's say I'm pulling on a string that's attached to the side of the wheel, right? And so that's the direction that I'm pulling. One way to find the torque is to take the 2 vectors from the picture and redraw them so they start at the same point. Right? And so that's this picture. So there's F, I can move it, R, here, they start from the same point. There's an angle between them. That angle is the theta. You can write RF sine theta. So not a different angle, right? So basically not this angle that's like F away from the vertical, right? But the other part. Another way that's really common to think about this is similar to what I said for angular momentum, where I said, oh, you can take the velocity and do a straight line and find out how close it gets to the axis. Now, you can't picture the force as moving along the straight line at different moments in time, but the same idea works because it's also a cross product. Right, so I can take my F and I can draw an imaginary line that points along its direction. And I find the closest place to the axis that it gets. The closest place will be where there's 90 degrees between that line and a vector drawn from the axis to the line. And that's why it's called R perpendicular. If you can find that distance, like that might not be so easy on this one because that's just something in the middle of the circle, but that's also a way to think about it. In some problems, it'll be easier to think about it that way. We'll see one later today. The other way is sort of the complement to that. where you find the perpendicular force. So I take my radius out, and I imagine that's like one axis of a coordinate system, and then I draw the perpendicular direction to it. And then I want to find the component of F along that perpendicular direction. Right, and that's F perpendicular. Right, so all these ways will get you the same number for the torque. Right, but they might be easier for you individually or for a particular problem to visualize. Okay. All right, so next thing we want to do is just we want to practice some situations. And so I'm going to set up a poll, and we're going to just figure out the torque. So instead of getting an exact number for the torque, so like with an exact angle or having an exact distance, there's just going to be 5 options. So we're just going to think about, is the torque R times F, and is it positive or negative? So for A and B, your choices are going to be positive. For C and D, they're going to be negative. And I'm going to say that positive means counterclockwise. Okay, so that way we're all in agreement on which way is positive. A, the difference between A and B is that A, you have R times F. B, you have something less than that, but still positive. And then C is minus RF, and then D is something that's negative, but its absolute value is less than RF. And then E is that the torque is 0. And one thing else I want to mention when we draw pictures like this is commonly how you'll see it when you're doing a problem, right? That you'll have a wheel or a spool or a ball or a beam or something. You'll have some physical object that you know the dimension of. You know the radius or you know the length, right? And then there's a force, and maybe we'll tell you where the force is acting, or maybe you have to figure that out. So in this case, I've told you that the force is going to act right where the tail of that F vector is in the picture, right? And then you need to figure out what the right R vector is to find the torque, right? Because I've drawn on here a line for R and written little r next to it, but that just means that the radius of the circle is that R, right? That doesn't represent the R vector in the torque. The R vector in the torque is where the force is acting relative to the dot at the center. So that's the axis. Okay? So yeah, so take a minute to think about it if you need to. So for this one, which answer best gives you the torque? Okay, why don't we just take a few more seconds? Okay, 3, 2, 1. All right, so the favorite answer is A, which is that it's positive, and it's R times F, right? And this is right, because you can try sort of picture if you pulled that way that the circle, the wheel would want to go around counterclockwise, right? And then the R would be drawn from the dot to the tail of the F, and that's perpendicular to f. F is going tangential to the circle, so the radius, that r vector is along one of the radiuses of the circle, and they'd be perpendicular, so you get the maximum. That's right. Okay, so what if it looked like that instead? So the force is acting at the same place, and it has the same magnitude, but what if I changed the angle? Okay, why don't we just take a few more seconds? Okay, 3, 2, 1. Okay, yeah, so the favorite answer is B, which again is right? Because what's happened is you have the same position, right? That the full distance is still the radius of the circle, you still have F, right? But they're not perpendicular anymore, right? So you're going in a bit by an angle, still wants to spin in the same direction, so it's still positive, right? But you'd get less torque than RF, something in between 0 and RF, depending on exactly what the sign of the angle is. Okay, so we just changed this up a little bit. What about this one? Okay, let's do a few more seconds. Okay, 3, 2, 1. Okay, so the favorite answer is still B, which is good because that's the right answer. But there's a bit more disagreement this time, so let's make sure we talk through this in detail. Right, so the difference between this one and this one is just, they're actually at the same angle with respect to the vertical. Just one is out and one is in. Right? And so actually, they actually have the same torque exactly. because again, like they still want to make it spin counterclockwise, right? Just because it goes out a little bit, that part that's out doesn't make it want to spin any direction. It's just the part that's up that makes it want to spin counterclockwise. And then the fact that it's not perpendicular means you don't get the full RF, right? And then it's not 0 because it's still there's you draw the R and you draw the F. They're not parallel, right? And F is not acting at the center of the circle. So the only way to get 0 is basically to have it act at the center or to have it be along the direction from the center to where the force acts. Okay, so let's, I think, check that because that is the next one. All right, so yeah, so if the force acts at the center, what's the torque? Yeah, I'm going to do this one as a pretty short one. So let's just take a few more seconds. Three, two, one. Yeah, so E's the favorite. E's correct. So 0 torque, right? Because if you try to draw an R vector on here, you have nowhere to draw it. You'd have to be drawing from one point to the same point, right? And so there's just no distance. So when something acts at the center of the rotation, it can't cause a torque, which is actually a very useful thing for later in this week as we start to think about what axis we want to use. Okay, so what if I move the force to the other side? Samantha, the last one, do you mean this one where it was acting at the center? That one's 0. Yeah, because it's acting at the center. So there's no R vector, basically. The R vector is 0. Yeah, okay. So let's just take a few seconds on this one where it's on the left and going up. Three, two, one. All right, yeah. So the favorite answer is C. That's good. That's right. So it's like the problem we did, the question we did a couple ones ago, where it's the maximum the torque can be in terms of magnitude because it's all the way at the edge of the circle and and the force is acting perpendicular to that vector, right? But now it's going to make it want to turn clockwise, so you have to make it negative. Right, and again, and for this positive and negative, right, basically the way we've set this up in our class, we have to put in that positive or negative sign by hand. Right, we have to say, I have to think about which way it wants to make the thing spin. Okay, one more. So I have the force act not at the edge of, the wheel, but imagine this is like a solid disc, so I can pull right where I drew that F. Okay, take a few more seconds. Yeah, the slides should already have been on the website, on the calendar page. If the link's not working, you can let me know. I'll have to fix it later. All right, but why don't we just take a few more seconds here. Oh, okay. So about counterclockwise always being positive, that's generally the convention in math. I think is that's the way, because that's actually the convention of the right-hand rule, that like x cross y gives you z, and then that's counterclockwise. You can pick. It's like picking the positive and negative for your coordinate axis that we did before, like which way's plus x and which way's minus x. You just have to make sure you're consistent about which way's which when you have torques acting in different directions. Okay, so let's wrap this one up. 3, 2, 1. Yeah, so majority got this right, that it's B, right? R and F, and while they're perpendicular, right, the F is not acting all the way out at R, which is the radius of the circle. And this is a good one to remember, is that the difference between the dimension R, which is the radius of the circle, and sort of the position vector that you use to make the cross product, right, is that generally we're going to be giving you problems where you know the dimension of some object, and you need to figure out what the length of the vector is you should use to find the torque, which in this case is something like r divided by 2 horizontal. Okay, so once you got that right, I just wanted to reiterate it. Okay. All right, good. So that's the last one for that, and so we can cut there, and we'll talk a little bit about torque and angular acceleration.